And we looked at three, I guess, versions of equations of lines yesterday. In particular, the vector equation, which is a big one, and the parametric equations, which was is a kind of another big one, and those were both very new. And I did call it scalar. So you see now on your note that we call it the scalar, and it's like the old standard form of the equation of a line from grade 9. This is scalar. And so that's the third one, and we'll see a fourth one today as well. So you got to know all four. You got to know how to go back and forth between all of them and how to answer all the different kinds of questions that we can ask you. Something as simple, find a point that's on a line. Or maybe I say find a position vector. It's the same question. Find a point on the line, find a position vector on the line. It's the same question, but asked it a little bit differently. And you have to know how to do all of those in all four types, all four versions. And it might just look different, or it might be that in order to do this process, you have to take what you're given, convert it to one of the other types. So there's all these different ways that you know, or maybe that's not the most efficient way of doing it, but maybe that's the way you choose to do it. Right? So there's all these little things that, again, we ask you to do. Some of them are very simple and straightforward from grade 9. But then starting tomorrow, we start to do some new things very different to what we've done. Okay? So ax plus by plus c is standard form. If you were looking at y equals mx plus b form, a point slope form, those are all scalar versions. But this is the one that we tend to think of. And actually, back in grade 9, whenever I teach grade 9, I always talk about how standard form is like useless. It doesn't give us any interesting information. In order to get good information like the slope or the y-intercept or the x-intercepts, you got to do work. You got to rearrange. Y equals mx plus b is a useful version of straight line in the Cartesian plane. But turns out standard form, this scalar form, actually gives us something useful when we're comparing it to vector forms and working in vector space. Okay, and sort of useful is its direction vector m. I don't know why I called it m here. It really should be d, right? So the direction vector d is negative of the coefficient of y and then the coefficient of x. That's kind of useful. Notice that this is in 2 space, and this will become more important, and we'll be more aware of this tomorrow. This is a big mistake that people make. There is no scalar version in 3 space of a line. There is no scalar equation of a line in 3 space. So yesterday, all the examples we did were in 2 space, but some of the homework was in 3 space. It scales up very easily because the vector form, I don't think you need to write this down. Vector form in 2 space looks like that. Well, what is vector form in 3 space? Well, it's that, right? So it's very easy, and you can scale this up to as many dimensions as you like. You're very useful. Vector form is useful that way. Parametric form is similar. Scalar doesn't scale up to 3 space or beyond. So there is no scalar version. So that's another limitation and why we need another notation, some other way of talking about lines in other dimensional spaces. Okay. More importantly, I think, about scalar equation, this is how I would do it, is the normal. Now, you've done normal lines because when we talked a lot about tangent lines, and a tangent line is a line that touches a curve at a point, doesn't cross a line, just touches the line at a point. And the normal line is perpendicular to the tangent at a point. So perpendicular to the slope of a curve at a single point through that point, that's the normal line. So the normal vector is the same. Now, vectors don't exist in a particular location, so vectors don't cross through points. But we're not talking about curves right now, we're talking about lines. So the normal vector is a vector that is perpendicular to the line that you're talking about. And I think what's very useful is the normal is just the coefficients of the x and the y. That's very easy to do. And when you compare that to the direction vector, this is what I think you should understand. Because it's not about memorization, it's about understanding. Is that if you take the dot product of n and d, what are you always going to get? You're always going to get 0. And that's like a times negative b plus b times a. That's going to give you 0, right? So if you can get the normal vector, that's a more common thing that we're going to do. Again, it's kind of useful when you're talking two space and lines. It's really useful when you're talking about planes, which we start tomorrow. But I'm going to get the normal vector and then turn it into a direction vector. Like that's what I'm going to do, kind of thing. You don't have to do it in 2 steps, but that's how I think of it. Okay, so turns out standard form actually has this usefulness when we're comparing it to vectors. So here's some examples of some things we might have to do for the line with the scalar equation. Determine the direction vector of the line and the normal vector. So in fact, I would, even though I ask these in this order, I think of them backwards. I would find the normal first and then the direction vector after. Like that's just how I would do it. So the normal vector is just 2, 5, which means the direction vector is something with which when I take the dot product with n, I get 0. So what's it have to be? Negative 5, 2. Which that little equation that we looked at, it's the same thing, but like I just think of it like that. We know the normal is the coefficients in order. That's what you really want to know. And then you can use that to find direction vectors. Huh? Yeah. That would be another direction vector. It could also be negative 10 and 4. That is also a direction vector. It's not simplified, but it's also a direction vector, right? Yeah. Because it's a line, it doesn't. So those vectors aren't equal to each other, but they are all appropriate direction vectors for the line that we're talking about. So if you think about then the vector equation, which we're about to do, if I put 2 in for t with one direction vector, I would, to get to a point or a position vector on that line, I would have to put negative 2 in if I'm using the other direction vector, but I'd still get to the same place. And that's what it's all about, is having some expression that I can use that finds all the points on that line or all the position vectors of the line. Write a vector equation of the line. What do we need? Quick summary of stuff from yesterday. What do we need to find the equation of a line in vector form? And? Yeah, or a position vector on the line, or which comes from a point on the line. So, just like grade 9, how do you find the equation of a line? You need slope and you need a point. But in vector space, we call it direction vector and position vector. But that's what you need in order to find those. So we already have the direction vector. How are we going to find a position vector? What do you think? Anybody? We could use an intercept, yeah. So I would sub 0 in for one of these and solve for the other. It's going to give me decimals and fractions, which is fine. Maybe they're not that bad, but what's another way we could do it? Somebody said this morning, solve for y, like put it in y equals mx plus b form. This is what you would do in grade 9 probably, because in y equals mx plus b form, you can put values in for x and solve for y and get nice values. But like, let's be realistic here. Can I just by inspection figure a point on this line? Anybody look at that equation of the line and figure out what a point would be? Negative 9, and what? Negative 9 is not a point. 0, negative 9, no. Daniel? Yeah, that would work. So that would be like solving for an intercept. Anybody else? No? Oh my gosh. How about 2 and 1? 4 plus 5 minus 9 is 0. So a point on the line is 2, 1. I got that by inspection. 2 times 2 is 4, plus 5 times 1, which is 5, which is 9 minus 9. Just think about it, right? the left side equals 2 times 2 plus 5 times 1 minus 9, which equals 0, which equals the right side. Therefore, my position vector would be 2, 1. Direction vector we already have, negative 5, 2. And so my equation would look something like that. How do we write the parametric equations of the line? Moving back and forth between all the different forms is what we do a fair bit of. It just gets us used to using these things. Zach? Yeah, so it's like x equals the x part here, so 2 plus t times the x part here, negative 5. T times negative 5. And I write it like this. X equals 2 minus 5t. And y equals 1 plus 2t. There's the parametric equations. Different forms are useful for different things. Okay, part E is curious. Solve each of the parametric equations for t and equate them. What does that ask us to do? What does that mean? Solve for t. I think this should be straightforward. Okay. So let's try with this one first. What do we mean by solve for t? Like, quite simply, again, this is a grade 9 skill. Is that solve for t? That's what that means? Okay, what about the other one? And t, they both equal t, so they equal each other. Like, it's the same t. That's what the t means. Go back up to the vector form. When I put in a t, it's the same t for the x and the y. It has to be. I can't put in t for one t for x and a different t for y. Doesn't make any sense. Same t. If I make t 2, I'm finding another position vector or another point on the line. If I make t 3, it's 3 for x and 3 for y when I simplify this. So these t's are the same, and it's the same in parametric form. The t's are the same. And when we checked the other day for a consistent t, if t wasn't consistent, the point was not on the line. Remember we talked about that. Like, t is the scalar that has to be consistent. So these t's are the same, so they equal each other. Therefore, when it says equate them, it's saying do this. Now, this is not a thing that we're going to ask you to do, generally speaking. It's something you're going to do. Because, surprise, on the back of your page, it's the fourth version of the equation of a line that we talk about. And it's called the symmetric form, or symmetric equations. It's where it's x minus x naught and y minus y naught, and x naught, y naught is a position vector or a point on a line. Position vector to a known point on the line. And m1, m2, the denominators of each part, is a direction vector for the line, as long as they're not equal to 0. And I told you before, scalar equations don't work in 3-space, but symmetric equations do. Somebody this morning remarked that if you have an equation in symmetric form, you could just rearrange it to scalar. That's all it is. It's a rearranged version of scalar form. So yes, that would work. But This form works in 3 space if I add another one. And that can't be solved into like scalar form. That doesn't make any sense. I got 2 equal signs in there. How's that going to work? Symmetric form for us isn't going to be super useful, but it's another one that we look at. So you would not be asked to do this. You would be asked to write the symmetric equations or put the equation in symmetric form, right? And you'd have to know that this is what you do. Probably start with parametric, solve for t, and equate them. All right, so let's do a few things. So here's our first example that we're doing together that's actually in 3 space. Because we didn't do any yesterday, but like I said, I don't think you needed that help to do those examples yesterday. But it does become more difficult in 3 space, and starting tomorrow, we do more work in 3 space, and it does become more complicated as we add on new things. So we got a line that passes through 2 points. Write the vector equation of the line. What do we need for a vector equation of a line? We need position vector and direction vector. So how do we get each of those things when we're given 2 points? We saw an example of this, but it was in 2 space. How do I do it? Help me out.
You're going to find vector DC?
Yeah, so we're going to find a vector between those 2 points. That'll give me the direction vector. Very good. How do I find the position vector? Just use either of those points. So my position vector could be, I'll take it from C. And my direction vector. Now be careful, if you do DC or CD, be consistent. If you write CD, but then you actually find DC, you're going to force me to take a half mark off or something, right? Because you're being inconsistent. That direction vector would still work. It doesn't, we already talked about, it doesn't matter which way you go, but you can't write CD and then find the other one. So you got to know to subtract backwards. So this should be 2 minus -3 and -1 minus 0 and 3 minus 1. If you did it the other way around, that's vector DC. And as I said before, in 3 space, it's just x, y, z. Write the parametric equations. So I don't think you need my help for this, so you can go ahead and do that. Everybody good? Got that? Write the symmetric equations of the line. So remember, it's x minus x naught So I can take this from vector form. So it's x minus -3, which is x plus 3 over 5. Or you can take it from parametric. If you already have that, it's already broken up into its parts, right? So -3 over 5 minus 0 over -1. And, if you can simplify these, you'll often see that they become simplified. So y over -1 is -y. Similar to yesterday, the next question says, determine if this point, -5, -0.5, -0.51 is on the line. Simple idea, but working in 3 space compared to working in 2 space. How do you do this question? Like, carrying it out is going to be easy, but you need to know what this is asking and how are you going to look for it, how are you going to show your work, prove that your findings are true. So what are we going to do? Yeah, very good. Symmetric equation is already solved for t, so I'm going to use that just because it's the new one that we're using, and we can see it's already solved for t, so we could use those. So t equals x plus 3 over 5, but if x is negative 0.5, so that's 2.5 over 5, which is a half, and t equals negative y, which is negative 0.5, which is a half. So we're good? Well, it has to satisfy all 3, doesn't it? Of course. So that's a little bit of a new idea. That's not a stretch. That's pretty straightforward and simple, but absolutely that is a thing. So again, the t's are not consistent. So point E is not on the line. Not good enough that it satisfies 2 of them. It's got to be all 3.
Would it be correct to say that it's not on CD? Or like, should we not say that because CD only exists between CD?
Yeah, I would say, somebody asked a similar question this morning, like, do we call this L1? I mean, you can do whatever you want. You can call it L, you can call it L1. When you're talking about different lines in the same question, we're going to call them L1, L2, right? And we're going to have names for them. So you would say is not on line L1 or not on the, but in this case, we're just talking about a line. You could say the line that passes through CD, C and D or something. You could, but in this case, since we only have one line, I would just call it the line. Yeah. Okay, and what are some other things that we might do? How about determine if each pair of lines is parallel, perpendicular, or neither? How are we going to do that? Again, you need to know what this is asking. What's this talking about when it says that? Dot product of what, though? What kinds of vectors? Random ones? Huh? No, not necessarily. Direction vectors of the line. You want direction vectors of each line, and you're going to do things like dot product or whatever to look at the properties and see if they are parallel, perpendicular, or neither. Doesn't that make sense? But we need the direction vectors first. So for line 1, first I'm going to get the normal vector, which is just 214. Then I'm going to get a direction vector, and I'm going to simplify it to negative 7, 1. Because generally speaking, that's what we would do. But for this process, you wouldn't have to, because using negative 14, 2, and taking the dot product, that's just as easy. Don't you think? But generally speaking, if you're writing the equation of a line, you would use a simplified version of a direction vector. In fact, with the normal vector 2, I would think you would usually use a simplified version of that. Okay, line 2. What's the direction vector for line 2? How are we going to find that? Yeah, it's given, right? It's in there, so that's useful for vector. So this is direction vector 1. This is direction vector 2. Remember, you said dot product. What's that going to show us? So, and do you think they are? First of all, just by inspection, what do you think? Like, you got to show some work, but by inspection, what do you think? Are they perpendicular? We think so? I'm not so sure. Be careful. So this is going to be negative 7 times 7 plus 1 times negative 1. I think that's 50. Negative 50. Which should be 0. So they are not perpendicular. So what's next? Parallel or collinear? How do I find out if they're parallel or collinear? Cross product. How do you take the cross product in 2 space? You don't. It's not a thing. That's not going to help us in 2 space. You're right. If we were in 3 space, you could take the cross product. There's kind of maybe an easier way, though, kind of overkill. What would it be? We looked at this yesterday, I think. Yeah. Is there a K for collinear? Is there a K such that D1 equals K times D2? Is there? What is it, Daniel? Yeah, negative 1. 1 is the negative of the other. They're the same kind of direction vectors, but opposite to each other. So when K equals negative 1, therefore, line 1 is parallel to line 2. The lines are parallel or collinear. Technically, collinear for a line means something a little bit different from collinear with vectors, because vectors don't exist in particular positions. I think we'll talk more about this tomorrow when we start to really think about 3 space and some of the properties in 3 space. So parallel would be the right word to use here. They might be collinear, but that would mean something else. Okay, what about these two? So those were given in scalar form and vector form. Now we're given 2 in symmetric form and parametric form. But the idea is the same, isn't it? We still have to find the direction vectors and do the same process. Don't you agree? So for line 1, the direction vector, and for line, not plugged in. For line 2, the direction vector. How do we find them in symmetric form and in parametric form? Anybody want to help out here? Yeah, it's just, remember, this is from the definition that you have on your page. It's the denominators. And the other one? So the coefficients of the t term in parametric form. These are all the little things you need to know. They're not necessarily obvious. They're not necessarily intuitive. So this is what you're becoming familiar with over the course of these few days. And what does it look like? Looks like the perpendicular. So let's take the dot product. So don't just say that. Show it with the dot product. Negative 6 plus 6, which is 0. They're perpendicular. So your practice is basically the rest of the worksheet. Still just A and C for a few of them, but basically the rest of the worksheet from yesterday.